Hey guys, sorry it took me so long to get this going. I've had several surgeons appointments and doctor's appointments, and so anyway, here we go. All right, I'm going to try to finish chapter 5 in the next few installments. I'll be doing like 15-minute, hopefully 15-minute modules here, and give you a chance to digest them. You guys still, most of you still owe me by the end of today 2 homeworks. So let's get on that, right? We can't let our guard down now. We got just a few weeks to go. All right. So I'll be putting up lectures through the weekend, and we'll move into chapter 6 and hopefully get to 7 before the end of the semester. That's my goal. So anyway, we'll talk about the next exam soon, but for now, just stay up reading the material and doing and owning the problems. So so let's do it, right? So this is electricity and magnetism. And oops, I'm using Notability here, which is pretty nice little application for the iPad. So I'm going to call this E&M Chapter 5, Part 1. Okay, and so we'll just chronologically keep that kind of notation, chapter and part. All right. So I want to go back and as you guys know, I love the magnetic vector potential, and I just want to go back and look at a couple of examples, tease them apart, and try to explain them in a little bit more detail, and actually give you guys some added reading to do that will link with some quantum mechanics that you've done either in modern or actually in quantum mechanics, which I think some of you have taken. So let's go back. Let's not go back. Let's look at a problem which is of crucial historical importance. So this is a I guess an almost infinite solenoid. We can consider it to be infinite. So as a matter of fact, we can even get rid of the word almost, so so it doesn't confuse anyone. And so it has a steady current I, and it has a linear loop density. Of n, right? And that's number of loops per unit length. So that's number per meter. Okay. And if one were to ask you to find the vector potential, both inside and outside the solenoid, your first go would be to employ one of the equations for finding the magnetic vector potential. In this case, it would be mu naught over 4 pi. This would be K dot dA I'm sorry, K dot R caret over R. Now that can't be used in this case because the current has an infinite extent, right? And these equations are only they're only usable if the current dies off to zero at some length, and that's not the case here. So we have to find some other way to get at the vector potential. Okay, so so the way we do this is let's look now at the line integral of the vector potential around some circuit, around some closed path. And now by Stokes, we know that we can write this as del cross A dot dA. We recognize this as the magnetic field strength. And so this then becomes B dot dA. And you might recall by analogy, right, that the electric flux, and I don't know if you encounter that in the first 4 chapters, but you might have encountered it in university physics, and that's a long time ago. The electric flux is going to be the number of field lines that cut through some area. So it can be written as E dot dA. And so by analogy then, we call this the magnetic flux. And we might have met this in university physics too if we got to Faraday's law, which I typically do. So this is going to be the magnetic flux. Okay, and so then this is going to be defined as phi of B, and I'm not so sure that Griffiths actually designates this as with subscript, but I will. So what we have then is that in the integral around some closed path, A dot dl, then is going to be equal to the magnetic flux. Okay, and that's going to be our workaround for not being able to use this equation above. Okay, so let's begin to explore that just a little bit. So inside, one, so it's going to be inside the solenoid. Inside the solenoid, what we have is the following, right? So we have A dot dl, okay, and dl now is just going to be a circular, right? Is going to be a circular loop. So if we have, if this is some blow up of the solenoid, then what we're going to have here is, again, this solenoid is of radius r, and what we're gonna do is have a loop inside of radius s. Okay, and so the magnetic field, right? The magnetic field here is constant inside. Okay, and so we'll be able to calculate the flux there. So then this then is going to be this then was going to be A integral around dl. The dot product then will be will give you a cosine of 90 degrees. So if this is some dl, okay, and then I'm sorry, cosine of 0 degrees. A is going to be A will be along dl, right? So A will be in the same direction as dl. And so then that's going to give you a theta equal to 0 degrees. Cosine of theta then will be equal to 1. And so A is constant inside, okay, constant along this red circular path. And so then this is just going to become A times the circumference then, which is going to be 2 pi times S. All right, now we can calculate the flux. The flux then is going to be then B dot dA, which then is going to be equal to B is constant. B is constant inside, right? We know what B is, right? B is mu naught N times I in magnitude, all right? So dA then is just going to be equal to, right? This then the flux then is going to be equal to B times dA, and the area of that red circular loop is just going to be pi S squared. And B, we know what B is inside, right? It's going to be mu 0 in I times pi S squared, right? So putting those together then, we have A times 2 pi S. It's going to be equal to mu naught N times I times pi S squared. Well, the pi's will go. One of the S goes with one of these. And we're left with now that the vector potential is going to be equal to mu naught N I over 2 times S. Now, if we select cylindrical coordinates, right, then what we have here is this is going to be z caret, and then around that circular path, we're going to have phi caret, and then we'll have s caret along the radial direction. So then this will be then in vector, full-blown vector designation. This will be mu sub 0 n I over 2s phi caret. Okay, and then this is for s less than or equal to r. All right, and we'll check these. We'll check these later. But you know, if you took, right, as a check here, if you took the curl of A, you better get B, right? And you can check that, and we'll check that later. If not, you can check it. See how the time is when we get there. Okay. So now, what about outside the loop, outside the solenoid? Okay. So so outside the solenoid, right? We play the same game, right? So here's our solenoid. Right? We have radius R, And we're going to pick a loop, which looks like this. And that's radius S, okay? So we can use the same analysis here, right? If we look at A dot DL, then that's going to give us A. It'd be DL, right? Again, the dot product becomes a cosine of 0 or 1, right? And so then this, once again, is going to give us A times 2 pi S. The flux now, which is then going to be the integral of B dot dA. Again, B is going to be constant. dA then is just going to give us, this is going to give us now B, this is going to give us pi r squared, okay? And we know that B, the relevant B cutting through this area hasn't really changed at all, right? So this, there it is, right? There's no B out here, okay? So this is B is equal to 0. B is equal to 0, right? We got that before from Ampere's law, okay? Right? So that was from Ampere's law. And you should know how to do those arguments. And so this is going to be mu naught n times I times pi r squared, okay? And so if we let A 2 pi s be equal to mu naught n I pi r squared, the pi's cancel, okay? We're left with A is equal to mu naught n I over 2. So it's going to be r squared over s. And if we look at the vector designation for this, then that's also going to be a phi caret. And what you're beginning to at least appreciate is that the direction of the magnetic vector potential is the same as the direction of the current, okay? And that's invariably true, all right? So let's look now. Let's look at a check of these. And so del dot A should be equal to 0. And so if we look up, the divergence in the front cover, then this is going to be del dot A is going to be 1 over S, change with respect to S, ace of S, plus 1 over S, the change in A phi with respect to phi, plus the change in A Z with respect to Z. So now A has only a phi component, whether you're, and again, I should have stipulated that this is S greater than equal to R. So A, regardless of where you are, whether you're either inside the loop or outside the loop, it only has a phi component. Okay, so ace of S is 0, ace of Z is 0, and the ace of phi component doesn't contain phi as a independent variable at all. And so the change of, right, the change of a phi with respect to phi is 0. Okay, so so the divergence of A is equal to 0. Okay, so that that checks out, and so that's going to be regardless of whether you're inside or outside the loop. So this is going to be for S less than or equal to R, greater than or equal to R. Okay, so let's look now. Right, let's look at the curl. Right, let's look at the curl of A. All right, and the curl of A is going to be 1 over S, and we can look that up in the front cover now too. Once, hopefully, at least somewhere along the line, you've brute forced the derivation of both the divergence and curl in cylindrical coordinates and spherical coordinates. In spherical coordinates, it's not very easy to do. There are some more elegant methods, as I've said, and I think there might even be an appendix in Griffith's book. I actually forget it. There used to be in an older edition, but so this is going to be 1 over S, the change in AZ with respect to phi, minus the change in A phi with respect to Z, and that's going to be the S caret direction. So it'll be plus the change in AS with respect to Z minus the change in AZ with respect to S, and that's in the phi caret direction. You have plus 1 over S, the change with respect to S of S A phi component minus the change in A S with respect to phi, and that's in the Z caret direction. All right, now again, knowing that that A only has a phi component, right? So this goes to 0. The change in the A phi component with respect to Z, right? Z is not in the vector potential equation, right, as an independent variable. So that goes to 0. All right, so this, for the same reasoning, that goes to 0. There's no AS component. There's no AZ component. And so we're left to the last with this last term here. Again, there's no phi. There's no phi independent variable in, nor is there an AS component. So we're left with now just we're left with this term. All right. So if we go back and look at, right, S times ace of phi, which you know is going to be then mu naught n I over 2. So it's going to be r squared over s times s. All right, and so then the s's cancel, and this gives us then mu naught n I over 2 times r squared, right? And these are all constants. And so then the change in S with respect to S times A phi is just going to be the change with respect to S of a bunch of constants, which is equal to 0. So what that says is that outside, now this is for, right, this is for outside the loop, right, outside the loop. This is for S greater than R. So for outside the loop, the curl of A is equal to 0, which means that B is equal to 0, right? This is for S greater than R. Let's look at inside the loop, right? So again, hopefully we won't have to rewrite all of that, right? So remember the only term that's going to survive that curl, right, is going to be this term. And so then what we have then is going to be 1 over S. It's going to be the change with respect to S times A phi, right? And that's going to be in the Z caret direction. So this is going to be then 1 over S. The change with respect to S. This is going to be S times mu naught I times, oops, let me change that. So this is going to be mu naught N times I. And that vector potential was S over 2 times S, okay? So then this is going to be equal to 1 over S, the change with respect to S. It's going to be mu naught N I, Z caret here, the S squared over 2. Derivative here, this is going to be then 1 over, whoops, let me just keep on forgetting to carry that around, that Z caret. That's going to be important, it's Z caret. So this is going to be 1 over S. This is going to be mu naught N times I over 2 times 2S. 2's go. And this then is going to be equal to mu naught N times I Z caret direction, which you know that the magnetic field inside is constant in the Z caret direction. So everything checks out, right? So this then is going to be for S less than R. So a couple of things really emerge here if you think about it carefully, right? So, you can have a vector potential. You can have a vector potential that's not equal to 0 that will give you a magnetic field which is equal to 0. So outside that solenoid, there is no magnetic field, but yet there is a magnetic vector potential. So I want you guys to go and read, whoops, it'd be good if I spelled it correctly. I want you guys to go off and read, right, the Wikipedia file on the Aharonov Bohm effect. Okay, now David Bohm is a pretty famous theoretical physicist, 20th century, actually born in Wilkes-Barre, Pennsylvania. So he's a native Pennsylvanian. And so I want you guys to actually to read, right, to read down to and including the section on the magnetic solenoid effect. All right. Now, this is probably one of the most important discoveries in quantum mechanics of the 20th century. Okay, so please go off and read that. It should be completely legible, not only legible but comprehended. Sorry, it's something you can comprehend. And so I would like you to read that, make the connection now between what you've learned in E&M in a rather simple problem and the impact it had in quantum mechanics and the far-reaching ramifications it had for quantum mechanics in the late 20th century. Okay, really important. So I'll pick it up from here in the next installment, and we'll just keep on pushing along. Okay, so thanks a lot, and talk to you guys soon. Enjoy this great weather. Bye.